Okay, so I am not going to teach any specific statistical method here today, but really just to go over some foundational concepts in statistics and epidemiology. And this is based on my teaching materials for teaching classes in the School of Public Health, but I also incorporated some ophthalmologic examples, especially based on my own collaborations and also reviews of manuscripts. And I think there are things that need to be commented on, and that will be very helpful in terms of applying these basic concepts in everyday research there. Okay, so this is the topics I'm going to cover. And feel free to stop me anytime. I tend to speak very fast, so I'm too fast, and feel free to let me know and I'll slow down, okay? All right, the first concept I want to talk about is a population versus sample. So these are foundational or very basic terminologies in statistics. The population here, it refers to all the subjects or phenomena that you are interested in. And for example, that you always have a scientific question in the back of your mind there. Like here, an example is that I want to study the height of residents in the US. This is my question. And then implicitly, the population of interest is really US residents. This is the population here. Now, in contrast to the concept of population is the concept of sample. This is the subset of subjects from the population that you are able to observe. So this is the reality, what you can observe. Now, the point of population versus sample is the population of interest is often too large, and you can't obtain for every subject there. So you can only sample some subjects from the population. The purpose here is that you can use what you observe, this is your sample subjects, to draw some inference about the population. So the population is essentially what you want to answer about the scientific question. But in reality, you only have a subset, the data set from your sample, okay? And the point mentioning this is that it's very important that using your observed data to correctly answer the population level information there, you need to have a representative sample. So here is an illustration, the example of looking at the height of US residents, that's the population. And I know in US, like for example, half are female and half are male there. But then in reality, I can only get the height information of a sample here. For example, 1,000 people provided a survey of 1,000 people that have the height information, and I found my data contains 75% are female. So in this case, using this sample data, this is what you really have. Using this data to infer for example, the population average height, then you can imagine it's going to be underestimating the population level average height there, right? Because females are normally shorter than male there. So this is an example showing that the sample is not representative of the population. And the results you obtain from your sample is going to be a biased, it's an incorrect answer of what you are really interested in at the population level there, okay? So the point to mention that here, that you have to make sure your sample is representative of your population. Otherwise, you are going to have a biased sample, and the results are not going to reflect the true feature of the population. So how to make sure this happens? Well, this really starts from the very outset of your study. If you're doing a prospective study, before you go to collect the data, at the design stage, think about all the possible situations or the issues that you might run into in enrollment, in follow-up. And you want to try your best to think of strategies that can help promote random sampling and promote you get a representative sample. For example, if people who, if like male patients are more likely to be lost to follow-up, then you want to think of strategy that can help prevent their loss to follow-up, the male patients follow-up at the beginning, like some kind of outreach activities. So that's at the design stage, something that you can think of to promote a generalizable sample that you can get later on. And then of course, reality is reality. What data you can observe is what you can observe. After you have tried your best, then at the analysis stage where you already are given the data set, then what you need to ask yourself is, do the characteristic of your sample reflect those of the population, okay? So that means you need to look at your data first to see what kind of people or what kind of sample you have from, and how well they, or what kind of population that the sample of your data can reflect there. And now statistically, there are also certain ways to deal with bias sampling there, but then that's really post hoc. So the ideal is that you want to start thinking about this potential issue at the design stage, okay? This is prospective study. And then retrospective chart review study or using electronic health records data. This is also very, very common, especially for the residents here. A lot of your research is actually chart review. And here I want to mention, particularly mention the importance of your data, your sample, and how well that can help you answer the population, the question of the population of interest there, okay? So normally when you do chart review there, there is a list of data inclusion and exclusion criteria there. I mean, the patients, their data are already there, it's retrospective, but you have to like assemble, it's still a sampling process. You have to assemble a data set for your analysis. So you define all this criteria there. But when you do this defining the inclusion exclusion criteria, you have to be very careful. And here I'll give you two examples. The first example, this is really from a manuscript that I reviewed last week. This is a very typical issue here. Now, the general theme, the scientific interest of this manuscript was to study the safety after receiving a specific kind of anti-VEGF injection in patients with wet AMD. Okay, this is a newly approved, FDA approved injection. So I won't mention the specific name of this, but this is, just know this is a specific kind of injection there. Now the safety, I mean, this is new approval, so certainly safety is very important to monitor at the real practice level there. Now specifically in this, as an example here, the safety is reflected as an adverse event, retinal vascular occlusion. So the occurrence after an eye start to receive this kind of infection, whether the eye will have this adverse event of RVO, retinal vascular occlusion here. This is the scientific interest, it's just laid out there. Then implicitly, this means that the population of interest will be all the eyes of wet AMD patients who receive this specific kind of anti-VEGF injection, right? So this is the population of interest that's at the back of the mind. They are defined based on the scientific question. So what the authors did actually was very smart, is to use the IRIS registry. Now, everybody here, I believe, knows about IRIS registry here. So this is more like a electronic health record, that kind of database there. Now, specifically, they retrieve the data for all the eyes that received this kind of injection during this time period, October 2019 to June 2020. Now, this is reasonable because, excuse me, this is reasonable because the injection was FDA approved on October 9th or 8th in 2019. And then when they did the analysis, it stopped at June, that was June 2020. So this is the data retrieval time period from IRIS. And then they have a list of inclusion exclusion criteria to specifically define what kind of data points about the injections for the patient that they are going to abstract from the registry and do the analysis there, okay? So one of the key data inclusion criterion was this: the patients has to have at least one, or the eye has to have at least one post-index ophthalmology visit. So the index visit is the visit where the patient first time received this kind of injection. And then they were receiving that the patient had to have one post follow-up visit available in the registry. And then in this case, they are going to retrieve the patient's data into their analytical data set. Now, here is a problem with this definition or this inclusion criterion where it's a sampling bias problem, where patients who experienced RVO will be more likely to have a follow-up visit and thus made to the data set. But patients who had no problem and thus did not come back by June 5th, which is the time of their ending of the data period there, those people were artificially truncated out from the data sampling process, okay? Why is this? Here is an illustration here where you can see this is their time period where they want to retrieve the data. And if I have two patients who started to receive this particular injection, say on the same date here, then the patient who tend to have an adverse event like RVO here, and then the patient will be more likely to come back timely, to be visited and to be seen, and then to be recorded in IRIS by June 5th. But on the contrary, the other patient who were much better off, the patient had injection, but the patient did not experience any adverse event, then the patient may not come back timely, and the patient then will not have a follow-up visit by June 5th. So in this case, this patient, the dotted line here, this patient data by the definition here, inclusion criterion here, this patient will be artificially left out in the data set or in the sample there, okay? So then you can imagine the sample data, the observed data really is more abundant with the patients who are more likely to have an adverse event of RVO here. Then in this case, using the observed data to estimate RVO incidence, then this is going to be an overestimate of this adverse event associated with this kind of injection, okay? So this is an issue of, or example of a bias sampling where the sample is not really truly well reflective of the population of interest there. And this actually can be avoided. This is a retrospective chart review. This criterion should have been just taken out there, and then the patient can, the authors can do other analysis to better analyze the data. So this is an example about retrospective chart review about sample, whether that's really reflecting your population very well. Here's another example. This was from my own collaboration on Stargardt disease research. Okay, so this is also a retrospective chart review study. The scientific interest is to study progression of atrophy in Stargardt disease and the atrophy, the lesion size as measured on fundus autofluorescence as shown here, okay? So the population here is Stargardt disease, and of course it's Stargardt disease, how it's diagnosed and how it's defined, that's another story there. So this is my question, my scientific interest and the population there. And the data are going to be a multi-center chart review study where the study team also define a list of chart review inclusion criteria, what kind of patients that they want to review their data and then get into the data set. So one of the criteria was this: males and females aged 6 years and older affected by Stargardt that have an atrophic lesion in at least one eye, with a sum of all lesions less than or equal to 12 millimeters at the most recent visit. So what that means, remember this is a retrospective chart review, so only in patients at the most recent visit, their lesion size was less than 12 millimeters, then they will go to the patient's charts and then abstract the data into the data set. Now here, this is also a problematic sampling process because here as shown here, imagine two patients. Now in 5 years ago, these two patients, for example, have the same lesion size in their eyes, okay? And then over 5 years, in the most recent visit, one patient was a slow progressor where the lesion size was less than 12 millimeters. Then based on this inclusion criterion, this patient, the data will be retrieved from the chart and entered into the data set. But then on the other hand, the other patient was a faster progressor where in the most recent visit, the patient's eyes, the lesion size was much larger than 12 millimeters squares here. Then in this case, this patient will not be retrieved because of the definition of the sampling process here. So this, at the end, then what are observed in the data set are really those slow progressors. So you can imagine that with those slow progressors, this is the data that you really have in the data set, then the estimation of the progression of lesion size is going to be underestimating of Stargardt disease in general, right? So this is another example, a very real example from my collaboration there. and that speaks to the importance of sampling process, especially when a lot of you do retrospective chart review. It's very easy to say, I want complete data by listing a lot of criteria there, but you have to think about when you define the list of inclusion exclusion criteria there, are you truncating the data that your sample is not going to be representative of your population and will not be able to correctly answer your scientific question there. So basically the point of population versus sample here is that you have to consider whether your data, observed data, your sample reflect the population of your interest. Or in another way, saying that once you are given the data, then you have to think about what kind of population your results, your sample can reflect, okay? So that's the generalizability issue. And this is a point that you have to consider at the study very outset there, as I mentioned earlier, at the design stage, either prospective or retrospective study there. And another thing to mention is that it is a good practice that when you write manuscripts there, your table 1 is always just a summary of your data, okay? A summary of the characteristic of the sample who are in your data. So like the 8 demographic and key clinical relevant characteristics there, just list out before you do any fancy advanced statistical analysis there, always just list the characteristic there. And this will give your reviewers or your readers a sense of what your data, what your population, what your study sample are, and what kind of population that your results can reflect that they can apply to, okay? So that's population versus sample. And related to sampling here, I want to mention one thing is about the sampling units, okay? So basic statistical method, the fundamental statistical methods that are really derived for data that are sampled from independent units. So data points from different people or different units are supposed to be independent, okay? But in ophthalmology, this is specifically a setting where it's very likely that your data are sampled from units that are not are correlated. And in this case, I mean, the sampling is sampling there. At the analysis stage, then you have to take care of the correlated nature there. There are certainly advanced statistical methods that are dealing with correlated data there. Now, here are some examples where correlated data can arise, like for basic science researchers, if you are observing the same eye of an animal, but you take out you measure different sections of the same eye, then the measurements of the different sections, those are certainly correlated data, okay? And then clinical or basic science, then eyes from the same subject, from the same person, or from the same animal, those are the data are also going to be correlated. And also animals from the same litter, those measurements are also going to be highly likely to be correlated there. This is more like in human, this is more like a twin study, or from the same family, same family origin there. The measurements are going to be correlated, and you have to account for the correlation in the analysis stage. And this is because like imagining if we're talking about the 2 eyes, the data from the 2 eyes of the same person, the amount of information, data information in those 2 eyes is certainly very different from the amount of information available from 2 independent eyes, okay? So that's why at the analysis stage, you have to look at the sampling, the unit there, whether to determine whether correlated data analysis methods are going to be needed, all right? So this is the first point about population versus sample there, and I will move to the next concept about random variable. But before that, is anything to talk about here? Any question? Great. So I'll move to talk about a random variable. Okay, so this is another concept that I want to comment on. Random variable, this refers to a mapping of a real world phenomenon to a variable. Its value is random. So this is very straightforward there. Like height, you can just use X, or RVO occurrence, this is Y, just denote that using a letter there. But the things I want to comment on is the random variable, the thing that you are studying, you should explicitly define that What I mean by this, for example, I want to study SARS-CoV-2 incubation period. So the real world phenomenon, the thing of interest is the incubation period for this virus. But then there are different ways to define it. For example, exposure to the virus, the incubation period could be the time from exposure to testing positive, or the time from exposure to symptom onset. So clearly these two periods are going to be different. So which one to use? I mean, that's not a statistical question. But the point is that when you say that you are studying incubation period, then you should clearly define it, how this variable is measured, okay, how it's defined, and you should list it in the method section there. And another point, another example of this, how this needs to be explicitly defined is, for example, I want to study visual acuity after an intervention there. Now, then the variable that you can define for visual acuity, actually there are different ways. For example, you can just study the visual acuity at the follow-up, like 1 year follow-up after this intervention. I mean, then your random variable is the visual acuity at 1 year follow-up. Or alternatively, you can also study the change of visual acuity between baseline and the 1 year follow-up. So apparently the change of visual acuity is still about visual acuity, but the random variable defined here, the quantification is totally different. So this, what I mean is that when you have a real world thing that you want to study, when you want to analyze that, this thing, how you are defining this real random variable related to this real world phenomenon that you have to, that you need to clearly spell that out, okay? Things like visual acuity or change of visual acuity, this is actually related to in clinical trials, that a big thing in the design stage is outcome measure selection. So that is the specific, what kind of outcome measure that needs to be very clearly defined at the design stage. And similarly, if you are writing up the manuscript there, then write this very clearly, even in the abstract there, okay? Another thing about random variable to comment on is a type of random variable. So, and this is determined by the values of random variable, like categorical random variable. This is the case like gender or marital status. Clearly, the possible values for this thing can only be a finite number of categories there. So this is categorical variable, and then in contrast is a quantitative random variable, including continuous variable like age or fundamental autofluorescence lesion size. This is certainly a continuous numerical values for the random variable. So why this is important? I mean, most often this is pretty straightforward when you have a random variable there, but still it helps that you think a little bit before you analyze the data to understand the nature of the variables you're interested in, because the type of random variable or what kind of values they take, these are going to determine the specific statistical methods you are going to use, okay? So for example, that everybody knows about logistic regression, and then you will know that's the case when you have categorical random variable there. And linear regression, that's another very well-known model there. That's the case that you analyze for continuous variable there, okay? Another thing about random variable, I mean, we're talking about one random variable, but when you do analysis, of course, you have a lot of things, a lot of variables that you want to analyze. So every relevant variable, you should always summarize that, and I'll mention that again very soon. So another thing about a random variable to mention is distribution. So the concept of distribution of a random variable describes what values it can take and how often these values can happen. Okay, so the point here is that you determine the random variable, the aspect of real life that you are interested in, and you also determine the population you are interested in. This is driven by your scientific question there. But what you observe is really the values of the random variables that are from your sample subjects, okay? So the essence of statistical analysis here is really that you use the data you observe from the sample to do kind of some summary, to do some kind of analysis, so you can infer the corresponding characteristics at the population level there, okay? So again, this goes back to sample versus population there. Now this is about random variable. And as I mentioned at the very beginning, we are not going to talk about any specific statistical methods. But I will mention that it's very important as table 1, the first step when you're given data set before you do any statistical analysis is to first describe your data or just look at your data, not to do any more analysis yet, but look at the variables that you are interested in. One is to see what kind of characteristics of your sample, and the other is really just to get a sense of your data, okay, like outliers. You might even identify some data entry error there, okay. So how to describe your data, this is pretty straightforward, so I'll flip through very quickly there. Graphical methods for describing your data. If we're talking about categorical variable, then like distribution of marital status, then you can just tabulate that. Like this is marital status that has 3 possible values: never married, currently married, and ever married here. And then you just tabulate, show the number and percentage in observed in your data set. And other graphical methods is like pie chart or column chart, or this kind of stacked column chart. This is, again, everybody knows about that. And the only thing to mention is the pie chart is most of journals actually don't like to see pie chart. This is of course very useful in presentations, but in publications is more often this kind of column charts here. But regardless, this is a way to see your data, to look at your data. And the other thing to mention about graphically describing is really the plots that you can use to look at quantitative variables, okay? Graphically looking at quantitative variable, one way is, for example, if we're talking about the age, this is certainly a continuous variable, but you can still tabulate that if you self-determine some kind of cutoff values. So you are grouping the age into different categories and then just tabulate that. Now, this is one way to summarize your continuous variables. And you must have heard that it's not recommended for continuous variable to categorize that. Apparently, there's a loss of information if you are grouping a lot of values of age into a big chunk there. And it is true, it's loss of information. But actually, this is not uncommon in epidemiology for variables like age. And this is because it's still sometimes it's useful in implementation. Think about if you have to do some kind of program like screening for diabetic retinopathy, for example. Now, when you go to the community to do the screening there, you have to have a defined population that you want to do the screening, like age. I mean, you don't want to screen for age younger than 50 or 60 there, right? So you still have to have some kind of cutoff. So I guess the point here is that even this is a quantitative variable, you can still categorize that to summarize that, but the cutoffs, of course, should be meaningful to your specific study context there, okay? And a quantitative variable.
So let me just, I want to clarify. So to go back one slide, these bins are different sizes, right? So it's okay to do that as long as there's a plausible reason for it. So for like just the age 50 to 29 is 15 years, from age 30 to 50 is 20 years, and is that okay to do?
Can you hear me? Yes,
yeah,
you can, right? So I'm trying to adjust the volume, and it was a little bit cut off, and probably the internet there. So could you say it again? The cutoffs, the age.
Right. So these bins or these categories, they have different sizes, right? They're not different sizes in here or something like that.
Robbie, you've got a lot of echo.
Huh.
That's the issue.
Why? Okay. All right. Can you still hear me? Is it better? Okay. Speakers are echoing. The main question was that in this example here, the different categories are of different sizes, right? The first one is 15 years, the second one is 20 years, the third one could be very large. And is that okay to do when you're doing descriptive statistics versus like erring on the side of equal kind of bins? sorry, Dr. Kong, I'm gonna.
Yeah, you hear me, right? You can hear me? Yeah, that's an excellent question. And that relates to the cutoffs should be meaningful. So the short answer is you don't have to equalize the bins there. Now I put it in here. This is more. I should give you more a specific context here. This is in HIV epidemiology field. The age is sometimes you'll see the age is defined in these categories. And this is because of the HIV, thinking about HIV prevention. The age can be defined because this is related to the risk level of HIV infection. So based on the sexual activity level of the people there, then this age group is somewhat a reflection of how sexually active, and sexual activity, of course, is related to risk of HIV infection. So the cutoffs are defined, not necessarily that you have to equalize the sample size within each age group, but really related to the specific, it's related to the specific context to define that in a meaningful way there.
Okay, thank you.
Okay, so then quantitative variable histogram. This is another way to tell you that you can, to help you eyeball your data as a very first step there. Okay, so what histogram is, most of you probably are familiar with this, so just very quickly. The histogram, this is showing the distribution of one random variable, which is on the x-axis, life expectancy. And the y-axis is just a summary of at each value of life expectancy, how often that was observed in the data set. And this is actually in the data set, the unit was country. Each country has a certain life expectancy there. So from a histogram, you can certainly get an idea of the frequency or of the distribution of this random variable observed in your data. Like the minimum is 55 years and the maximum is about maybe 78 years of life expectancy of countries there. And by the shape, you can also get a sense of how the values of this random variable are distributed in your data there. So histogram. And then another plot is scatter plot. The scatter plot is also very often, I mean, everybody will know that this is very straightforward. The essence here is to use that to eyeball relationship. So in scatter plot, you definitely involve two variables. The x variable here, the x-axis is an example, the variable is annual growth of the country. And the y-axis, the variable is life expectancy. So by looking at this kind of scatter plot, certainly you can get a sense of how the x variable is related to the y variable there, okay? So scatter plot is especially useful when your scientific interest is about studying the association of different variables there, okay? So in regression setting, this is a first thing that you should do to see, for example, whether the y variable is linearly associated with the x variable there. Now, related to scatter plot, it's another, a little bit special kind is in statistics, we call that as the spaghetti plot. So this is the case where the x variable is time. This is follow up in months there, and the y variable is another random variable, like here, mean sensitivity here. Now, this data is really like a longitudinal study where you have repeated measurements of the same person or the same eye here. And then you can use this kind of spaghetti plot to visualize within person or within unit, within eye trend over time there. So each line is the measurements within an eye. And this is actually a very helpful if your interest is to look at over time how things change, okay, to help you eyeball your data before you do any further regression analysis there. Okay.
What program was this created in?
This is SAS. All the statistical software can do that. I think, I don't know, probably you guys use more often what, Prism is, right? Prism, I think it can only also do spaghetti plot. Although I'm not sure whether it's called spaghetti plot there. In statistics, this is called spaghetti plot. or series, maybe series plot there. All right, another plot I want to mention to help you eyeball your data is a box plot. And again, this is more familiar here. Now, this is looking at the distribution of one variable. And again, this is life expectancy. So the box plot shows us the distribution where the box in the middle is the line in the middle is the median. And then the box is defined by the first quartile and the third quartile. So what quartile means, it's the first quartile is that if you look at the corresponding value here, probably about 68, then that means about 25% of the data points in your sample are having a life expectancy lower than 68 there, okay? So this is the box. And then these are called the whiskers, and the range of the whisker, the range of the whiskers is defined by 1.5 interquartile range, where the interquartile range is just the height, the middle 50% of your data point, the values there, okay? And then this is you will see data points that are outside of the whiskers. These are more like outlying data points or extreme values, and in this case, there's only one data point that is extreme, but in most often cases, you'll see quite some data points that could be outside of the whiskers there. So this box plot can show you the distribution of a continuous variable. And it is particularly helpful, and you can use that in presentation and manuscript there, is to show you the comparison of a continuous variable by group here. So this is still the life expectancy, but I'm comparing the life expectancy of countries by group, and the group here is defined by region. So this is Europe, Central Asia region, and North American region, and South American region. So by this is a way to help you eyeball whether, for example, the average life expectancy in a region in the world, whether it's different across different parts of the world there, and also the variability, like the how different the country's life expectancy within a region. And you can also eyeball this, get a sense when you use box plots here, okay? So these are some graphical methods for describing data. And then next, I'll talk about basic numerical methods for describing data. So again, these are things that you can consider to use when you do your table 1 to provide characteristic of your study sample there. Now, if it's a categorical variable, then you just tabulate, summarize the number or proportion of each category of the variable in your sample there. And then for quantitative variable, the like lesion size or age, the values are more variable. There are more information in those kind of quantitative variable, okay? So there are different aspects about a quantitative variable that you can summarize about your observed data. And there are different aspects are really defined by the scientific question there. Now, most often, if not all the time, the primary interest is on the centerness of the values. So that's a measuring of the center here. Then the statistic one to use is the mean. Now this is, again, everybody knows about that. The mean is, if X is a random variable, then its sample mean is estimated using the data observed on the sample. It is an average of what you observe. And then the point, of course, again, is that you want to use the sample mean to infer the true mean at the population level, which is unobserved. And that's why you want to make sure, again, going back to the first point, that you want to make sure your sample is a good reflection of your population there. Now, how to estimate the sample mean? This is if you have n subjects and n values about this random variable like age, then you just take the summary and then divide it by the sample size there. So nothing special here. This is the mean. And then the other measure of centerness is the median. So this is another statistic here that you can use to show to see the centerness of the variable there. Now the median, I think everybody here knows about the median too. This is just the middle value among all the observations that you observe for this random variable. Okay, so for the median, that if you have n subjects, you just arrange that from small to large, like lesion size, from smallest to the largest, and the median value is the middle value of lesion size, where 50% of in the data, the lesion size will be lower than that median, and 50% will be larger than the median there. And this is the specific way to estimate the median. Again, this is a sample median based on what you observe there. Now, the thing to mention is about mean and median together. Now, these are two different statistics. Both can reflect the average or the centeredness of the distribution of a variable there, okay? But they are different things. They are different statistics, and they have different properties there. Now, in the case, if your random variable, it has a symmetric distribution, you can think of the histogram we just talked about will look more symmetric. Then in this case, the mean and median, they are the same. The values are the same. But if X has a skew distribution where histogram will look more skewed to one side, as shown here, this is the more skewed on this side, but of course it can, another distribution can also skew on this side. In this case, the mean will be different depending on the skewness, which direction, then the mean will be different from the median. So when your variable of interest has a highly skewed distribution, then you may consider using the median as a central measure rather than the mean there, okay? But there's no golden rule here. And sometimes I've seen people who present both median and mean, which is certainly helpful too. So that's the centeredness of a continuous random variable to look at the average, that aspect of the data values. Now, another important aspect of the data values of the random variable is the spread. That is reflected by the statistic called the variance. And the sample variance, this is what you calculate from what you observe. The sample variance measures how far each observation is from the mean. So it is a measure of dispersion, okay? The larger the variance, the more variable of the potential values of the random variable. So when we say that there's a lot of variability in visual acuity, for example, visual acuity is the random variable. Variability, a lot of variability in visual acuity, that means reflected on the statistic, that means the variance of this random variable is very large, okay? The sample variance, how to estimate that is based on this, where for each value, like visual acuity for the first person, you compare to the sample mean. And then the square of that, this is the distance, right? This is the dispersion there. And then you average over, and the denominator here is n-1 here. So this is the sample variance. Now, related to the measure of spread, more popular, you have heard of a word called the standard deviation, this statistic. Now, this is also a measure of the spread. It is really just the square root of the variance, okay? But most often people use the standard deviation as a reflection of the sample dispersion there. Here, a little note is the variance and the standard deviation, they are defined in relevance to the mean. So when you use the mean as the measure of center, then the measure of dispersion should go with the variance or the standard deviation here. Now, another thing about spread is the interquartile range. So this is going back to the box plot. The interquartile range is just defined by the first quartile and the third quartile. So the interquartile range, then how large that is, it also reflects how much spread is in the data there. Now the interquartile range, then within this range, that means 50% of the data points values are within this range, okay? So this is the measure of spread if you are using median as a measure to reflect the centeredness of your data, then the spread, you can use the interquartile range to show the variability there, okay? All right, and then of course, there are other different aspects about your random variable when it's continuous. There's a lot of properties there. And you can also use percentiles, more flexible, using any percentile to describe the spread of your data, like the quartiles where the 25th median was 50 percentile there, but you can choose other percentile depending on your specific context. Like in the like birth weight, that's a birth weight. That's an example here where what is of more scientific interest is to look at the extreme low birth weight. Then in that case, you probably care more about the first percentile of the birth weight there, those really extremely low birth weight infants there. Right, so these are different measures to describe your data that you can use to summarize the data characteristic. Are there questions? No. Okay, then I'll move on to talking a little bit about parametric distributions. And this relates to probability, but I won't go into, and you certainly don't go into the probability aspect, but I just want to give you a sense of, you've heard of normal distribution and chi-square distribution. What can you use those for, and what they really mean there? So for even a random variable is random, there can still be some kind of rule existing based on the distribution of the possible values. And knowing the rule can help summarize the observed data, okay? So for example, here, if we want to know the chance for a country to have, say, life expectancy of 65 years old, this is my scientific question. In this case, then only knowing the center and the variability of the distribution of life expectancy is not going to be enough. You will need to know more about the distribution. And this is the case where knowing the distribution rule will be helpful. And this distribution rule in statistics or probability has a name, that's the probability distribution, okay? So probability distribution of a random variable can describe what the possible values of the random variable are and how probabilities are assigned to these values. And there are probability distribution, there are a lot of parametric distributions or there are a lot of names there. And I want to give you a few just very commonly used parametric distributions just to give you a sense. And when you say a name of a specific distribution, then it's tied to a specific kind of random variable, whether it's categorical, whether it's continuous, and if it's categorical, what kind of feature it has, okay? So that's why I want to give you a sense by mentioning the very common distribution names. Like the first one is binary distribution, a Bernoulli distribution, and you should know this if you have worked on logistic regression there. So Bernoulli distribution, this kind of distribution can be used to describe what kind of random variable. Well, this is really just a yes or no case where your random variable is just like gender, yes or no, male or female. It's random, but it can only take on two possible categories. So this Bernoulli distribution, in this case, is called binary or Bernoulli distribution. And the unknown aspect, the rule there is really focused on the probability, the success probability, like being a female, the probability of the next person coming in being female there, that probability aspect is the key of a Bernoulli distribution, okay? And then related to Bernoulli distribution is a binomial distribution. This is the case, for example, if I want to look at the number among a group here. Now, each individual to look at gender, and then I want to look at among a group of people, the number of females, for example. That number of females, that's a random variable. That variable will have a binomial distribution, okay? So this kind of random variable, the number of women in a group here, it can be described using a binomial distribution. And similarly, if you talk about, for example, the number of people who respond to treatment, that's also a binomial distribution. Now, by saying binomial distribution, then it has its own probability aspect there, okay? Like the 5 people responded to treatments, and then what is the probability of 5 people responding? Then there is a specific probability, a formula related to binomial distribution there, okay? All right, then there are other distributions for, there are other distributions for discrete data, like categorical distribution. This is the, if you have worked on generalized logistic regression, this is the case where your random variable is more than 2 categories, like marital status. It can has 3 categories: currently married, ever married, and never married, 3 categories. Then this is just called a categorical distribution. It's the rule with this categorical distribution is governed by the probability of observing a value of each category there. Now, Bernoulli distribution and binary distribution that we just talked about is just a special case where there are only two possible categories. Another distribution related to discrete data is Poisson distribution, and some of you probably have seen, like when you read the literature, you might see that like Poisson regression. That's actually related to Poisson distribution. So this is what kind of random variable can be described using Poisson distribution? It's really a count random variable. So if your random variable x takes values of 0, 1, 2. To infinity, so it's a count. It can only be a whole number there. Then it can be described using a Poisson distribution where the probability of observing a specific count is governed by this particular formula here, okay? Now you don't have to look into the specific formula here, but the point is really that when you are given the name of this distribution, then the probability aspect is all specified by the corresponding formula attached to this particular distribution there, okay? So when the random variable, it can be a count, but this is actually pretty common, like in epidemiology, that the number of disease incidents, the number of deaths, mortality there, and or the number of patients, or the number of cells, if we are talking about inflammation there, those all can be described using a Poisson distribution, okay? Right, so these are more for discrete data. Now let's talk about, give you a few names of common distributions for continuous random variable like age, lesion size. Talking about continuous variable, then I have to introduce a concept called density function. Now again, it's just to give you a sense what this means. The density function is one way to describe a continuous variable. It is a function that describes the relative likelihood for this variable to take on a given value, okay? So it's a specific probability formula there. Now the probability of x, this continuous variable, taking on any value in an interval, like lesion size between 5 to 12 millimeters, the probability of this size then can be determined if you are given the density function of this random variable there. Now, there are many different parametric distributions for a continuous variable there. The most common one is normal distribution that everybody has heard of. So here is the normal distribution, and this is the function form for the normal distribution. Again, you don't have to read into here. It's really that why this is this specific format, this is just defined if you're talking about a normal distribution. Now, the normal distribution is determined by two parameters, the mu and sigma here, that has particular meaning. The mu is really the mean and sigma square is the variance. So if you have a set of data like lesion size, and if you assume lesion size follows a normal distribution and you observe a sample like a different data there, different data points there, then you can use your sample average and sample variance to infer the normal distribution describing this random variable like lesion size there. That's the point of using parametric distribution there. And another thing important about normal distribution to mention is standard normal distribution, where the mean is 0 and the variability, the variance is 1. This is called standard normal distribution. So how you use it, this is actually related to p-value. But here, just for example, to be more intuitive example here, if I'm looking at the random variable of change of visual acuity, and I assume the change and standardized in contrast to its the change of visual acuity standard deviation there. Now, if this is my random variable and I assume that it has a standard normal distribution, then I will know by saying that it follows a standard normal distribution, then I will know people who the eyes who have who have an increase of 2 letters standardized, 2 letters of visual acuity, the probability for a person to have 2 letters increase is 2.5%. And this 2.5% or 2 here, or really 1.96 here, this is the area under the density curve of this normal distribution, okay? So this normal density distribution curve is determined by the formula that you just saw earlier, the density function there. And the area under the curve, more extreme change of visual acuity, more than 1.96 letters there, is 2.5%. So in another way, saying that a person's visual acuity change of more than 2 letters, either here or lost 2 letters, the probability of that is 5%. So if you are familiar with how p-value came along, then this is actually related to how p-value is calculated, where you have observed based on your data, you observe a statistic. I mean, a statistic here, like I'm looking at 1.996 letters here. Then the more extreme change of the more extreme change than about 1.96 letters there, that probability is 5%. So that's the area under the normal curve is related to the p-value, like from 2-sample t-test there. This is also how you use density function to get the p-value, to calculate the p-value. Now this is normal distribution, and there are other normal distributions, and this is just showing you whether it's high, low, fat, or thin. It's determined by the center, mean, and the standard deviation or the variance there, okay? But the shape is always symmetric. So bell shape is a defining feature of a normal distribution. Now, another distribution I want to mention is chi-square distribution. You don't have to read into this. The chi-square distribution, just knowing that a random variable, the values can follow a chi-square distribution. And the density function of chi-square distribution looks more like this, which is skewed. So chi-square distribution is now symmetric there. Now, why I want to mention this, again, if you have the density function given the specific chi-square distribution, the parameter is given here, then you will have the shape of the density function. Then you can also calculate the p-value as the area under the curve. And that is the p-value behind chi-square test, okay? The chi-square test that most of you probably know about, and that's specifically related to a specific kind of scientific question when you want to look at the association of 2 variables that are both categorical, they're chi-square test. So the p-value for that is coming from a chi-square distribution. All right, another distribution, t distribution, you don't have to read in this again. The t distribution is also symmetrically distributed. This is a density function. Now again, the area under the density function is going to relate it to the probability there. And this is how p-value is calculated from a t-test. So everybody should know what t-test is for. All right, there are many other distributions, as I mentioned earlier, like Weibull distribution. You might have seen this name in the literature there. So why we need this parametric distribution? When you say that a parametric distribution, it's really an assumption there. But there are also like statistically interim in the statistical steps there are certain derived statistics that follow parametric distribution, and those are going to be very important, very helpful. So why we need parametric distributions? When you just need a simple summary of the observed data for the variable of interest, like the mean, variance, or the specific parametric distribution will now be very important there. But if you need to do more complicated tasks with the data, like comparing 2 groups, this is certainly a very common scientific question there, like in clinical trials, whether intervention group compared to placebo group, whether it works, then this is a comparison, that kind of scientific question. Or if you want to study how one variable is related to another variable, studying the associations there, relationship there, then the parametric distribution form will be very useful. So they provide a mathematical tool to do analysis, to get p-values or get confidence intervals.